and I were to look at graphing polynomials, so this first lesson focuses on polynomials in standard form and some basic characteristics. So the first thing is the equation of a polynomial in standard form. So basically that means that the operation between each term has to either be addition or subtraction. These a's that I'm writing are going to represent any numbers. And then you can see that my exponent is gradually going to decrease. So then I would have like x squared plus x to the first plus our constant term. So it would be x to the 0, which is just 1, so I'm not writing it. So these a's with a little subscript, the subscript matches the power, and basically these a's are just going to be numbers. So these a's that I have listed here are all just numbers or coefficients. And then what makes this a polynomial is that the highest degree or the highest exponent's in front, which is why it's in standard form. But what makes it a polynomial is that it's addition, or these could be negative signs in between each of the terms. Now, when we say the equation of a polynomial in factored form, this is where we have maybe some leading coefficient out in front, or we have some factor out in front. So let's just say I have a single a, just some number. And then we express the polynomial as a set of parentheses where each one of these numbers here are going to be the roots. So in factored form means it's already been factored, and this is going to be helpful when we have to find the zeros, which is what we did in Unit 8. We had to set the equation equal to 0, factor it so that we could figure out the zeros. In some cases we couldn't factor, so we used quadratic formula, or we used completing the square, or we used the rational root theorem. So that's kind of where we'll be going, but this is just an example of a polynomial in factored form. So you could have as many roots, so I'm just going to call this root n, because if that was like the 6th root, as you want, it's just that's going to be the degree of the polynomial. So those are the differences. Factored form means you have the parentheses and you have the roots right there. And in standard form, it just means that you have the highest exponent first. And typically you're going to see your polynomials in standard form. Now, some characteristics of the graphs of polynomials: they're continuous. So that means that there's no holes in the graph, there's no breaks, they just keep going. So if you imagine taking your pen or pencil and tracing the graph, it would just keep going. So for example, this would be an example of a polynomial graph because it keeps on going, there's no breaks. They're smooth, rounded turns, so they have maximums and minimums. They go up, they go down. They rise and fall, but they never end. So there's always going to be arrows. So here's just some different examples of different polynomials. And then the last thing here is writing polynomials in standard form. So if you're given these polynomials over here, to write them in standard form means the highest exponent has to be in front, and then it goes in decreasing order after that. So this first example, it would be 5x to the 7th. Then the next highest is the positive 4x squared, and then it's the plus 3x, and then it's the constant. So the degree is the highest exponent. So in this case, it's a degree 7. And the leading coefficient is the number in front of the highest exponent. So the leading coefficient would be 5. For this next one here, I would have y equals, it's going to be a negative 2x to the 3rd plus 6x. The degree is the highest exponent, which is 3. The leading coefficient is the number in front of the term with the highest exponent, so we have negative 2. And then this last one is a constant. So in standard form, it's just going to be left as is. The degree of this, you have to really think of this as y equals 8 times x to the 0, because x to the 0 is just 1. So whenever it's a constant, the degree is just going to be 0, because the exponent of that variable would have to be 0. And then the leading coefficient, well, it's the same as the other ones. The number in front of the x, or just the number here, would be 8. So then let's look at some other characteristics. The next characteristic when we're talking about polynomials is having to do with their leading coefficient. So the leading coefficient, the whole reason why we just identified it is because that term is going to be really important. If it's a constant, it's a degree 0, then that just means that you're going to have, so if I have a set of axes, degree 0 just means you're going to have some horizontal line that's going through whatever that number is, whatever that leading coefficient is. So positive means the line's going to come up in the top half of the graph. And if it's a negative leading coefficient, that just means that your horizontal line will be down in the negative numbers. So these are my x and y axes here. So then if you have a linear term, meaning there's like y equals mx plus b, so this is like y equals mx plus b, so it's a degree 1. This one's like y equals some number. If I have my set of axes, let's just draw these in first. So then when I go to look at my line here, if it's a positive leading coefficient, meaning if this number here is positive, that means your slope of the line is positive, so it means it's going up. Where if that number is negative, that means your graph is going down because it means you have a negative slope. The next one is a quadratic, a degree 2. So your leading coefficient, so let's say I have y equals ax squared plus bx plus c. Your leading coefficient is this number in front of x squared. So if I have my set of axes, if I have a positive leading coefficient, so if that a value is positive, then my graph opens up. So that means my end behavior here, or the arrows, are both going up. I always think of it as, okay, I have a smiley face because it's a positive leading coefficient. If it's a negative leading coefficient, you have a sad face, or you have your parabola opening down. And again, this is a degree 2 because the highest exponent is a 2. A cubic. So let's say I have y equals ax to the third plus bx squared plus cx plus d. So again, my leading coefficient is that a value. And for this one, the shape's going to be a little bit different. So if that leading coefficient, so that a value is positive, that means your graph is going to start down and then come up. So the negative portion of the graph is down in the negative numbers. The positive portion of the graph is over in the positive numbers. And then it's switched for if that leading coefficient's negative. So that means now I have it going down, and then it continues to go down. So everything's basically just flipped. Again, degree 3, so the highest exponent was 3. And then the last one that we're going to look at is a quartic, which just means a degree 4. So, for example, y equals 8a times x to the 4th plus bx to the 3rd plus cx squared plus dx plus e. So let me draw on my set of axes. And for this one, whenever you have a quartic, it's really going to follow that same rule as the degree 2 or the quadratic, since it's an even degree. So if the leading coefficient is positive, that means both ends of my graph are going to go up. Where if my leading coefficient's negative, both ends of my graph are going to go down. And there's times where quartic equations might look similar to a parabola. So what that means is I could also have graphs that look very U-like. So it could just be like a wider U. So quartic sometimes doesn't have to have all of these loops, but the main thing here that we're trying to get out of this is that the ends are both going up for positive, both going down for negative. Same with quadratic. So these follow the same pattern. Same with cubic. So cubic is a different pattern, but if you do like a degree 5, it's going to follow the same pattern. If you notice, it kind of follows the pattern of a linear. So if it's positive, it goes up. Your ends go in that same direction. Negative, your ends go in that same direction. So whatever the degrees are, so odd power degrees are going to follow the same, and then even power degrees will follow the same kind of rule. So let's just summarize this rule on the next page. So this is called the leading coefficient test, which just basically means whatever that leading coefficient is, if it's positive or negative, and then the degree of the polynomial, if that's whatever degree number, that's going to depend how your end behavior is for these graphs. So our whole goal here in the end is going to be actually being able to be given an equation of, let's say, a cubic function or a quartic function and have to sketch the graph. So right now we're kind of just doing a part of it. So the leading coefficient test, also known as the LCT, so leading coefficient test, means that if I'm given some polynomial, so let's say I'm given this polynomial here, oops, minus 1, x to the n minus 1 plus, so this is just like our standard form polynomial equation. So if I'm given that, and I know that n is odd, so n is going to be the degree, because if you look, see how n is the highest exponent and it's in front in standard form. So n equals the degree here. And the leading coefficient, this is like the a sub n value here, that's this. So if n is odd, that means if the leading coefficient is positive, so think about the chart on the previous page, that means if I have this scenario, if n is odd and the leading coefficient is positive, that means you have this general shape here. So that means as x goes to infinity, so as x gets bigger and bigger and bigger, the y value gets bigger and bigger and goes towards positive infinity. So y is going to positive infinity. As x goes to negative infinity, y goes down to negative infinity. So this means it's a positive leading coefficient. That's what it's saying. The leading coefficient is greater than 0. This one is saying, well, what happens if the leading coefficient is less than 0? So what happens if you have a negative leading coefficient, but the degree is still odd? So that means one end's up, one end's going to be down, but it's going to be flipped. So that means if I have my graph, one end's up and the other end's down. So then when I go to look at this scenario to fill in the blank, as x goes to infinity, y is going to negative infinity. And as x goes to negative infinity, y is going to positive infinity. So they're always opposites. So the main thing is when the degree is odd, one end is going to be up on your graph and the other end is going to be down. Okay? When it's even, that means your ends do the same thing. So if you remember back to this chart, even degrees, both ends are either up or both ends are either down. Positive means they're up, negative means the ends are down. Where odd power degrees, it's always opposite. One end up, one end down. So when we go to fill this in, if we have, so let me just get my axes drawn on. So if the leading coefficient is positive, that means you have something like this, where both ends are up. So as x goes to infinity, y is going to infinity. And as x goes to negative infinity, y is going to infinity. So both ends do the same thing. And if the leading coefficient is negative, so that means something like this. As x goes to infinity, y is going to negative infinity. And as x goes to negative infinity, y goes to negative infinity. So both ends do the same thing. So for even, both ends are up, or both ends down. For odd, you always have one end up and the other down. If it's positive, the right side's up and the left side's down. If it's negative, the left side's up and the right side's down. So now that you know that this is a leading coefficient test, now if you see an example where you're given an equation and you want to determine a general idea of what the graph looks like, you can use this test to help you. So this set of examples here says use the LC test to determine the right and left behavior of the graph. So if I look at this, I have to identify what's the leading coefficient, what's the degree. So the leading coefficient, I'm looking at the highest term, or the highest exponent, which is 4. So the leading coefficient of that term is 1. The degree of this is 4, because that's the highest exponent. So I have a positive leading coefficient and an even degree. So that means both ends have to do the same thing, and since it's positive, both ends are up. So the general idea of my graph means both ends are going up here. So to describe it, you would say y goes to infinity as x goes to infinity, right? As x goes to the right, y gets bigger. And y goes to infinity as x goes to negative infinity. And then if we look at this other example, now I'm looking at this term here because the exponent's 5. So the leading coefficient is negative 2.1. The degree is 5. So that means now I have a negative leading coefficient and an odd degree. So that means if you were to look at the general sketch here, it would look something like this. So negative leading coefficient means this side's up, this side's down. Odd means you have opposites, one up, one down. So now when you go to describe it, as x goes to positive infinity, y is going to negative infinity. So y goes to negative infinity as x goes to positive infinity. And y is going to positive infinity on this side as x goes to negative infinity. So that is really a good way to get a general sketch. We will look in more details of how we make, the middle part more accurate, because right now you don't know if this graph looks like how I originally drew it, or does it look something more like this? We don't know yet. So right now all we know is how the end behavior happens. Same with this graph. This graph could have really looked something like this. So we're going to look more details throughout this unit as to how do we get the best looking sketch of these polynomials without actually putting them in a calculator and graphing them.